So one of the first differential equations which was developed was the Navier-Stokes equation. If you are a student of a branch of engineering called fluid mechanics or a branch of engineering called thermal engineering, you would most likely come across this equation. This is a very complicated equation, but then based on certain applications and certain assumptions, it can be simplified. And I know it looks very scary because this is the most general form of the Navier-Stokes equation, which helps us understand fluid flow as well as heat transfer. This particular equation that you see is basically a continuity equation in order to calculate the velocity of the flow of a fluid based on its density and the time which has passed from the start to end and so on. Navier-Stokes equations, even to this day, 200 or 300 years after they were first written down, after they were first discovered, they do not have a pen and paper solution. They do not have what is called an analytical solution. No one can sit down and take this equation and show us a way to get the final answer, which can be claimed to be the solution of this differential equation. Well, if this differential equation has not been solved, then why do we use it? Well, as I said, the pen and paper solution does not exist. The analytical solution, the exact solution of this equation does not exist. But then there are techniques by which we can find an approximate solution, a solution that is approximate enough to the exact answer to this question. And in order to solve this equation with approximations, we use computers, because the approximate solution of this equation involves doing lots of calculations, millions and millions of calculations to get the answer close to the actual supposed analytical solution. And even the approximate solution of these equations help us find out the solutions to a lot of practical problems, and that's why they are still used, even though, as I said, they are approximate solution. The word approximate doesn't sound good, but then approximate solutions can be made as close to the actual possible theoretical solution as possible, and this helps us a lot. Another differential equation. This is another form of the Navier-Stokes equation. This is for the conservation of momentum. As you can see, there are lots of strange symbols that you're not familiar with yet, but then in the ultimate argument, this is still a differential equation which can be solved to understand the flow of fluids around various obstacles and how to control the flow of fluids. As you can imagine, if we can know how to control the flow of fluids, we can design better aircraft, better ships, better boats, better submarines. And with that, of course, we can get to our destination faster, right? Another differential equation, another set of differential equations which are very famous and which help us live a much easier life compared to someone 400 years ago, are Maxwell's equations. Maxwell's equations of electromagnetism are the foundation of everything that we know in the chapter, in the topic of electricity. So right from the power that you get in your homes to the power that runs the trains and the planes, different appliances. You can think of almost nothing today that does not work on electricity or does not have any connection to electricity. So therefore, all of these objects have derived their applicability, they have derived their application from electricity, and electricity, as we know today, can be controlled by understanding and solving Maxwell's equations. In some simplified forms of Maxwell equations, we can get analytical solutions, but their most general form do not have solutions, just like the Navier-Stokes equations, because mathematically the structure of these equations is too complex. There are many such famous differential equations whose solutions have not been found yet, and there are many mathematicians and theoretical physicists who are still working on attempting to solve the most general forms of these equations because of their wide-ranging applicability.